The equation that predicts the universe, a scribbled formula on a chalkboard, would soon explain everything from planets to photons. It is a surprisingly familiar image, isn't it? Often invoked in movies and stories about scientific breakthroughs, representing the potential to unlock the deepest secrets of existence with a single elegant. For centuries, humanity has yearned to find a unifying theory, a single framework that could explain the seemingly disparate laws governing the universe, from the swirling galaxies to the smallest subatomic particles. The idea of a theory of everything isn't merely a fanciful dream of theoretical physicists, but a genuine scientific pursuit fueled by the belief that nature operates according to fundamental principles. One of the most ambitious attempts at achieving this unification is string theory, which proposes that the fundamental building blocks of the universe aren't point like particles, but tiny vibrating strings, much like the strings on a violin. These strings, vibrating at different frequencies, would manifest as different particles, phi electrons, quarks, photons, phi, essentially creating the rich diversity of matter and energy we perceive. Think of it this way: a single violin string can produce a multitude of notes depending on how it is plucked or bowed. Similarly, a single vibrating string could give rise to all the particles we've identified through experimentation. While this concept appears abstract, it elegantly attempts to reconcile two pillars of modern physics: general relativity, describing gravity and large scale structures, and quantum mechanics, governing the behavior of particles at the atomic and subatomic levels. General relativity beautifully explains the motion of planets and the bending of light around massive objects, successfully predicting phenomena like gravitational lensing, which we routinely observe today. Conversely, quantum mechanics explains how atoms interact and reveals the probabilistic nature of reality at incredibly small scale, showing that particles don't always have defined properties until. However, these two theories, while incredibly successful within their respective domains, clash violently when scientists try to combine them, creating mathematical inconsistencies and rendering predictions. Unreliable string theory emerges as a potential bridge, offering a framework where gravity emerges naturally from the interactions of these fundamental strings rather than being a separate force requiring its own computation. This framework also eliminates the need for point particles, which inherently lead to infinities in calculations within quantum field theory, a major stumbling block when trying to combine general relativity and quantum mechanics. Furthermore, string theory requires extra dimensions beyond the familiar three spatial dimensions and one-time dimension we experience daily, a concept that seems bizarre but might actually be necessary for the mathematical consistency. These extra dimensions, curled up at incredibly small scales, are beyond our current ability to directly observe, analogous to how an ant crawling on a power line only perceives one dimension while the line extends far beyond its perception. The equations within string theory are immensely complex, filling volumes and requiring sophisticated mathematics to even begin to understand their implications, often represented with elaborate symbols and Greek letters that might appear intimidating at first. Researchers have been attempting to find experimental evidence to support string theory for decades, utilizing powerful particle accelerators like the Large Hadron Collider to search for clues in the behavior of high energy collisions. While no definitive proof has emerged thus far, researchers are actively exploring indirect avenues, such as searching for subtle effects in the cosmic microwave background, see the afterglow of the mathematical framework of string theory also suggests the possibility of a multiverse, proposing that our universe may be just one of many, each with its own unique set of physical constants and laws. This concept challenges our very notion of uniqueness, suggesting that the conditions we observe in our universe may be just one possibility among an infinite array of potential realities, a mind boggling proposition. However, it's important to acknowledge that string theory remains a theoretical framework, awaiting experimental validation, and it's not without its critics who point to the lack of testable predictions and the challenges in connecting it to observable phenomena. Despite these challenges, the ongoing research into string theory pushes the boundaries of human understanding, forcing scientists to develop new mathematical tools and explore novel concepts about the nature of space, time, and the very fabric of reality. As you gaze up at the night sky, consider the possibility that the dazzling display of stars and galaxies might be just a manifestation of incredibly small vibrating strings governed by a single yet profoundly intricate equation, perhaps. Someday, a future generation of scientists will fully decipher this cosmic equation, unlocking the ultimate secrets of the universe and revealing a deeper understanding of our place. Wouldn't that be a breathtaking moment, witnessing the culmination of centuries of scientific endeavor? The unveiling of a formula that, in essence, explains everything we know and wonder about the cosmos.